Should be starting the stream now. Thanks, folks, if you're joining me. Just trying to get my lights to work properly. I have all kinds of issues over here. That one's working. Yow. Just going to turn myself to this green screen. I hope that works well. Oh, it's a bit blown out. Oh well. It's the best we're going to get for today. I have troubles with this webcam. Things used to work better with this system, but the software for this webcam stopped working well with macOS, so now I find it hard to control it. Now I'll go back to the holding screen. Thanks for joining me for a minute, but we can just be on the holding screen, and I'll be ready to start the lecture in a minute. Almost ready to start. Check that things are working. Ooh, I wonder if they are. Ah, it's live. That's great. I'm watching it. You know, I'm giving this lecture here from my office. Things get a bit hectic towards the end of the semester when we've got all of our assessments and our final few tutorials and lectures getting organized, and everyone's getting prepared for exams, and then there's a public holiday suddenly. So my lecturing timetable gets completely thrown out of whack with all of those extra unnecessary variables. And as it turned out, I just wanted to be able to do this lecture from the comfort of my office here in the Hannah Neumann building. And because, unfortunately, I don't use my office lecturing system too often, things get a little out of date and a bit janky, so it's unfortunately not the best technically best lecture I've ever done. If you want to see some of the technically best ones, they were the ones I used to do for Comp 2300 and Comp 1720 when I had a whole system that was working beautifully with no issues. But at the moment, I have issues and it's not working beautifully. Just make sure I've got all my stuff that I need on my screen and not things that I don't need on my screen, and then we can get ourselves started. Got one person watching on YouTube. I wonder if there's anyone watching on Twitch. There's a few folks on YouTube, a few folks on Twitch. A small but committed audience. Thank you to those folks who are joining me today. Just close off that lecture stuff. I only just finished the notes for the lecture as well. Updated the notes, so I'll just commit that and push it. And then the next thing I'm going to open is our coding notebook for the week. I've got a live coded notebook that I was working through with Yichen Wang, one of my PhD students who's just submitted her thesis. And this notebook will be what we're looking at partly through the day. And we'll probably have a little bit of an investigation of some of these concepts. All right, get rid of YouTube. Now that I know I'm streaming, I don't need to worry about things anymore. Go right back to the start. Hello. Welcome to the lecture. Let's go to the start recording. I started the recording, so hi folks, welcome to the lecture. I'll just turn the brightness down to minimum brightness. It's like, it definitely needs a little bit of light support in this. Oh, it works better if I'm over there, doesn't it? Definitely need the light support if I'm giving a lecture. I might grab another light and see if that will just even it out. The issue is sometimes not that the lights are wrong, but that the, where'd that light go? Oh. Just grabbing another light. I'm looking at myself on another screen, trying to see if this makes any sense. That's the side which is sort of dark. Nah, it's just ending up all washed out. These, or maybe this one. My little mini light. I'm not giving the lecture and I'm hassling with my lights again, or hacking around with lights again, which is just a classic Charles thing to be doing, isn't it? Okay, put this side light here. If I was more prepared, I would have done this earlier. Make that brighter. Turn it up to pretty bright. Oh, that's kind of even. Okay, here I am. We're now going to do the lecture. Folks, thank you for joining me if you're watching online. Thank you for the goats finally live again. Thank you, Mob, who's on YouTube. It's great to be teaching online again. I love teaching online, actually, because I get to sit in my cozy office. I get to have my setup exactly the way I want it. It's a great experience, I think, for you folks to see some code happening on the screen. And even if it's only a few people here, we get a great recording for everyone to watch afterwards and can deploy it as I need it. So I like to do at least one lecture online, even if we are mostly in the cinema this time. Here we are for statistical analysis. Now, we've already done one lecture on statistical analysis, and the point of coming back to statistical analysis is to dig a little bit more deeply into some of the tests we can do that might be used if we are doing a HCI research study or evaluation, comparing different kinds or the responses of different groups of people or the same person measured multiple times with different interfaces. And we can go through some of the main kinds of significance tests that would be used in these situations. This is a little bit of an extension topic because unless, or for many of the situations which you would be in the projects in this class, you'll only have a few participants. So unless you're doing lots and lots of repeated measurements of their data, you won't have a very good need to use a significance test. So although it is possible that you could use these in your final project, it may not be particularly appropriate, but they'd certainly be appropriate if you're going on in HCI to do a research study or an honours study. And they also would be appropriate in other fields where you're doing measurements, measuring some empirical data and trying to work out if you're seeing a real difference. So let's continue. A few little announcements. We have the final project specification available. That's been available since last week. I know that folks have started the final project. I know that folks are talking about the final project because I see questions that I'm trying to keep up with on the forum. The final project repo is not available yet. Hopefully we'll have that available to you on Monday along with the rubric, all the details of the rubric for the marking of that project. Assignment 2 marks will be out next week. We're looking at Wednesday. That's the official mark release date. The tutors are working hard at grading all of your assignments, so I think we should be able to make that deadline, but hope you'll forgive us if there's a little bit of a small extension required if something goes wrong there. So what's going on over the next 2 weeks is starting to change a little bit. Week 11, next week, is the last tutorial. So I've just pushed that tutorial on Canvas and maybe making a few tweaks later today. But that's the last sort of new content for the tutorials in this class. please make sure you get to that one. It's a really great tutorial that will get you thinking again and a bit more deeply about qualitative analysis. For week 12, we are doing the same times, but they're drop-in sessions just to look over what you need to do in your final project. So I would expect that everyone would have a good question or want to get together with their research cluster to do some work on their final project and evaluate everybody else's prototypes. So the time will be available then. The tutors will be there to support you in doing that work in week 12. Finally, the weather, although today not that nice, it is starting to get nice. Make sure you go outside. If you're watching this lecture, pick up your device and go outside and watch it there. It's great that we have getting some sunlight in the evening and afternoon, and the temperature is getting higher. So a nice time of year, even though I know it's a bit stressful in these last few weeks of the semester. So plan for the class. We're going to do some data analysis, more data analysis tasks. Some of the background here is to look at contexts of use and assumptions of different methods of analysis. We will have a little look at things like interpreting results and justifying validity. Maybe it's a little bit overstated at that point that we'll be doing that, but understanding the main kind of significance tests is the goal of this lecture. And then we can look at that in terms of a case study from some of my real research. We're looking at a different textbook in this class, so if we're interested in this, look at the textbook by Lazar called, what is it? Research Methods in Human-Computer Interaction. Nice to be in my office because I can just pick it up. Is this book. This one is also available as an ebook, so you can check that out easily if you want to get some information. This textbook is good in explaining what kinds of statistical methods you will want to do in an HCI context. In fact, explaining all research methods across the board. It doesn't tell you how to code those methods up in Python or R or SPSS. So it leaves that to you to figure out or to use a different resource. I'll provide you some hints in this lecture as well if you want to go that direction, but it's something that you would need to do some more investigation for if you needed to use these techniques. So just to come back to where we left off in week 5, when we get some data in our HCI studies, typically there'll be an entry step in turning it into something we can use in our software. And we experienced this already in our last lecture because we had to turn data coming out of Poll Everywhere in completely the wrong format into something in Python and Pandas that we could operate with. So that was, it was a real live lecture experience of the frustrations of that when I got the data out of Poll Everywhere and it was completely wrong, and we had to kind of vibe code something up that was going to help us get it in the right format. It's certainly important that we are careful about entering data. This is something you will need to do in your final projects. Make sure that you're keeping things consistent, looking at what you're entering, hopefully not getting errors if you're entering a large amount of data, being quite careful about what you're getting. I have discovered in the past with paper-based survey forms that a participant just forgot to fill in a question, which was certainly a little bit frustrating in the moment when I'd found that during my PhD. Later on, whenever I do a paper-based survey, I make double check that everybody has filled in every question before taking their survey paper away, because I had to throw away some data in that instance and it mucked up some parts of my analysis. But these issues with data can happen at any stage, so we have to be careful. We've done a bunch of that in week 5. For preparing data, again, this was stuff that we tended to do in we did before. We would be doing basic checks, make sure data is correctly grouped, finding any problematic data and maybe considering removing that. Sometimes we need to change something from some text to a numerical code. So the format we got had the response as like the like it response, saying strongly agree. Well, that was great, but I really wanted it to be numerical. So 5 for strongly agree, 4 for agree, 3 for neutral, 2 for disagree, and 1 for strongly disagree. Sometimes it's a good idea to organize your data into a sensible format. For instance, if you have to submit your data as part of your final project, it's good to make sure that you're not sending you're sending data which is already organized on the expectation that someone's going to read it. That is me. um, I've certainly had to do this in the past, take some data that I've hacked around with for a study, gotten the results I needed, but then wanted to publish the data as part of the publication. So I had to do another level of organization so that it was ready for potentially someone else to look at when it was being archived. And then another little revision on descriptive statistics. And this was kind of where I left you for week 5. We were basically looking at measuring where the center of a bunch of data was, a measure of central tendency, and then thinking about the spread of that data. So the measures of central tendency would be describing where the data is clustered, finding what the representative area of that, or the representative location of that data is in its range. And the 3 options we had were mean, median, mode, and the one that I really considered most relevant is the median. It's usually a very robust central statistic to use. But in this lecture today, we often look at the mean instead of the median. For the spread, we were measuring how much the data varies, looking at how much they differ from that central tendency. And our options were the range, so the maximum to the minimum, the variance, which is sort of a description of the average difference from the mean, and standard deviation. Our other important one were the interquartile range, so the 25% above, 25% of the data above the median, 25% of the data below the median, and looking at that in a box plot. And that was what we considered to be most useful. Again, that is still the most useful to me for many of the situations we have in HCI. Very useful to look at the interquartile ranges and the upper and lower bounds of the data with a box plot. But when we're looking at significance testing, we're really thinking about comparing means, not comparing medians, and not comparing the interquartile ranges. We can do that just from a plot, but for comparing means, we have these extra, more complicated ways of doing things. So why do we compare means? If we're evaluating with 2 groups or conditions, we want to know whether the difference between those groups that we measure is meaningful or not. So this is a bit like doing chemistry or biology, borrowed the same image from week 5, where we might have given half of our participants an interface with menus and the other half of our participants a command line interface, and we might measure their performance at a task. So we might have a hypothesis, which is that there is a difference in the performance, whether they're using a command line interface or a Windows pointer interface. We often have different kinds of designs for experiments. One of the very important distinctions is whether we're looking at between groups design, whether we would have participants in separate groups that only see one option for those interfaces, or a within groups design where we have participants in one group and they all see both options. And we discussed in the previous weeks how if you're looking at a within groups design, you might need to balance the exposure to those interfaces so that it can automatically, or the experiment design automatically accounts for the learning effects that might be occurring, where if someone sees command line interface first, they're getting a little bit better at the task than if they'd seen the other way around, or half the participants see the command line first, the other half see the Windows first, and then you switch them onto the other interface so that the effective learning is accounted for in the outputs. So I guess an important question is why do any of this stuff? Why can't we just compare means? So it might, if you compared their performance, like maybe group 1 performance was 86% and group 2 performance was 87%. And you might say, well, great, 87% is higher than 86%. That's a great result. We're a winner, our research is complete. But that 1% difference may not actually be meaningful. It might be a random variation. And just as an example, we could think whether a height difference of 20 centimeters is meaningful. So if we're talking about adult people, and a particular group of people tend to be 20 centimeters taller than another group, Well, that's quite a big variation, isn't it? Because normally a 20 centimeter difference in height is quite significant in a population. But if we're talking about eucalyptus trees, 20 centimeters is just like whether the wind is blowing and a branch is slightly higher or not, right? With people, maybe a 1 centimeter difference would be hard to detect because, like, well, if someone had used gel in their hair and it was 1 centimeter higher, they might be taller. But a 20 centimeter difference would be a huge difference for people. So the means don't account for the variance of the data. With eucalyptus trees, there'd be a lot of variance. It would be hard to take a measurement where a tree was measured accurately up to 20 centimeters, just because wind blows the leaves and they keep growing over time. Whereas with people, the variance of adult heights would be around in that bound of 20 centimeters. So what do we do about it? Well, the normal thing we do is to use statistical tests, which would help us to distinguish the variance from just random effects in the world. Measurements might be random depending on the time of day, or whether someone's, if we're dealing with measuring people, how they're feeling that day, what experiences they might have had before, etc., to the variance that's due to our experiment. So whether changing the interface has some explainable influence on the performance of the task. So the outcome of a lot of statistics tests is often something called a p-value, and it's not always clear what a p-value really is. So I've got a slide to attempt to explain that. P-values get thrown around a lot in scientific fields where we're dealing with empirical data. What p means, it's the probability of obtaining a measurement by chance given the existing distribution of measurements. So if you've got a distribution of measurements which is something like this normal distribution, so there's a set of possible results. If you just take observations from your regular population, they tend to be in the middle here if it's a normal distribution. Many things can be modeled by a normal distribution. But down either end, they'd be very unlikely to get one of these observations down at this end, and very unlikely to get one over on this end. So if you were measuring people doing a task and someone had a measurement down this end, you might think, oh, well, that's unusual. I wonder if that's because of something we've done in our experiment or whether it's just random. So the p-value helps to make that precise. It's the area, if our observed data point is here, the p-value is trying to measure the area under this curve between here and the end. So a low p-value means that there's a low probability that the difference of this data point from the mean happened by chance. And a high p-value means that there is a high probability that it could have happened by chance. So if your observed data point was very close to the mean and you just had a single observation, the p-value is going to be quite high because it will be very, there'll be a lot of variation in observations around this part of possible results. So another sort of value that gets thrown around in reporting results is this cutoff for p of 0.05. So that's often called a typical cutoff for significance. So if you do some statistical test and your p-value is less than 0.05, people say, oh, it's significant, or you can pat yourself on the back and say, we've reported a significant result. And the question is, why is it 0.05, and is this a good choice, and what does that even mean? Well, 0.05 is just kind of a nice round-sounding number. That's basically telling us that there's a 1 in 20 chance that something could have occurred by chance, according to our statistical modeling. And I guess that's a reasonable bar for deciding that something was probable, that it's a significant observation, and that gives us some some good evidence that a observation is supporting our hypothesis and rejecting the null hypothesis that something was just randomly occurring chance. But it's just a choice, and other choices are often valid. Many people use 0.01 as a cutoff point for p-values, even 0.001, a 1 in a 1,000 chance that it could be a cutoff. And some of this depends on the structure of our data and our tests, as we'll see in a little while. But again, 0.05 is just a choice. You can change that choice if you have good reason to and if you can explain it. Another bit of data which we'll find out in a minute about is this idea of degrees of freedom. So significance tests often involve estimating, well, they always involve estimating probability distributions, and that involves this concept of degrees of freedom. Degrees of freedom represents the number of independent values that you can vary in your analysis while still calculating the statistic you need. Now, I'm not a statistician, and it's not really a statistics course, so please don't ask me more questions about degrees of freedom because I really confuse myself trying to understand it or explain it to others. But broadly, the idea here is that if you have more samples in your measurement, then you have more degrees of freedom, and that's good. And if you have fewer samples, you have fewer degrees of freedom, which is bad. So if you have few samples, your low degrees of freedom, that will mean that your complex tests are going to use up those degrees as they're trying to establish a statistical model. And you'll then have a higher p-value because of the way that these models work. So having fewer degrees of freedom requires a stronger test score or a test statistic to reach significance because you don't have as much information to make these judgments. If you have a high DF, then you don't require as much of a strong test statistic to get a very significant or a very clearly significant outcome. This has goods and bads. If you have a lot of data, you can end up finding that everything is significant. And if you don't have much data, you can find out that nothing is significant, or nothing can be shown to be significant with these models. So often when we're reporting data, you might report your test statistic as well. As an example, if you've got a t-test, you might record a t-statistic of 2.45, but the t-score is not useful unless you know the degrees of freedom. You actually can't calculate the p-value without the degrees of freedom as well. So if you know that you've got 2.45 as your t-score and you've got 28 degrees of freedom, then you've got a p-value less than 0.05. If you don't have 28 degrees of freedom, if you've only got 5 degrees of freedom, then your p-value may not be lower than 0.05, even if you have the same t-score. So it's important to report that data. A little menu of significance tests. So I think we already talked a little bit about t-tests, but today we'll just go into a little bit more detail about two different types, the between group comparison and the within group version. So the between group version is called the independent samples t-test, and there's a paired samples t-test as well. We'll also talk about this group of tests called ANOVA, or analysis of variance. So there's several versions here listed. We'll talk a bit about one-way ANOVA, the normal one, and then the more complicated ones, the factorial ANOVA, and for repeated measures as well. The repeated measures is for within groups comparisons. So the important thing here is that t-test is good if you've got two groups. You can compare one group to the other group. If you've got more than two groups, you need a different test. You could do pairwise t-tests, group 1 versus group 2, group 1 versus group 3, group 2 versus group 3, etc. Well, that's it. That would be fine, but that also, if you're doing multiple tests at the same time, you will often have to do correction of the outputs, which means inflating the p-value, which means you risk not seeing the significance that you were hoping for. Whereas an ANOVA procedure can look at 3 groups and tell you if there's any significance at all just among those 3 groups, not specifically which groups it's between, but it will tell you if there's significance due to an effect of the experiment. all of these tests are for continuous or parametric data, so normal kinds of numbers, and assume that the data is normally distributed in some way. So now we get to some specifics. T-tests in HCI are used to compare means between two conditions, for instance, like performance or the time it takes to select an item in a menu. When we're reporting this, we will report the t-value, the statistic output, the number of degrees of freedom, and the p-value. So the normal, or a typical level of evidence would be to say, if your p-value is less than 0.05, that would be taken as evidence that you can support your hypothesis with this test. A smaller p-value, e.g. less than 0.01, would indicate some stronger evidence supporting our hypothesis. There's no perfect evidence supporting a hypothesis. Just some evidence is stronger than others. So the two tests, it's independent values when we're looking at samples from different participants or different things we're measuring. Paired values when we've got the same participant measuring multiple observations. And now we're going to do some examples. So I've got an interesting data set that we've prepared for you, which is a lot of data about songs on Spotify. I'm just going to make this a little touch bigger, which is going to make things massive. We've got songs on Spotify, and I think it's data about like 175,000 songs. So we actually have heaps of songs to look at. And we're going to do some statistical tests with this data. So I'll just load up some libraries. We've got matplotlib, numpy, and pandas, and load in the data. It actually took 300 milliseconds to load it, so that's a decent file. We can look at some of this data. I think someone scraped a bunch of data out of Spotify some years ago before all of these such APIs were removed. So we've got information about different kinds of songs and some data about them, which has been calculated, I think, on Spotify's end and then shown up in this data frame. So things like a loudness score, which is in decibels, a mode score, which is whether it's major or minor key, a popularity rating, release date, speechiness, not sure what that is, tempo, valence. So you could use this kind of data to do a recommendation engine, or for generating playlists, or for doing maybe like genre recognition or emotion recognition in songs. Lots of typical machine learning tasks. I think this data came out as part of or was used in part of a Kaggle machine learning challenge at some point. We're going to use it for some HCI testing, just for fun. Energy, explicit is whether there are rude words in the song or not. So this one doesn't have rude words, but this one does, by Mixer. Anyway, Screaming Jay Hawkins. I was about to say I don't know who any of these artists are, but I know about Screaming Jay Hawkins. I Put a Spell on You. It's a classic. We've got lots of data, 175,000 rows and 19 columns. So plenty of data here to muck around with. There's a few, this is just in case you were interested in all of the different types of columns here. There's some explanations of all the values that have just been put in, and doing a little bit. I'm just running these cells just to run all of the pre-processing. Most of the stuff we're not using. We're just using the numerical data and a few of the codes, like whether it's explicit or not. And here's some descriptive statistics. So for danceability, the median is 0.548 and the max is 0.988. So it looks like this has been normalized between 0 and 1. The duration, we've got some scientific format, but that would probably be in seconds. And the energy, wait a minute, that's maybe, oh, it's in milliseconds, that's why it's in scientific format. The energy, again, min 0, max 1. 50, the median is 0.46, so it's been normalized. The key is, I think, representing the musical key, whether it's A, B flat, B, C, D flat, D, etc. Liveness, again, all normalized data. So I suppose that's useful for machine learning. It may not be a good expectation that you have normalized data in HCI. So far, I haven't seen any sub chat. No questions, but good to know people are listening. Some basic analysis. Max loudness. This is a number in decibels, so 0 would be the maximum, and anything lower than 0 would be normal. Min loudness, -60, which is, that'll be a very quiet song. Different kinds of things. Don't need to look at all of this. I want to get to the bit where we do some tests. Okay, independent samples t-tests. So we've got a hypothesis here. The hypothesis is that we're going to compare two independent groups, all the songs that are explicit and all the songs that are non-explicit. So the hypothesis is that there is a difference in energy between explicit and non-explicit songs. Good hypothesis. We can ask a question of the data. The null hypothesis is that explicit and non-explicit songs have the same mean energy. So we can just have a little look. The energy would be a kind of analysis of the loudness and spectra of those songs over time. So we can have a look at a plot, generate the plot, histogram of energy by explicit flag. So looking at this distribution, it looks like there's tend to be a mean for non-explicit songs down here at 0.2, and there tends to be a mean for explicit songs at 0.7. So on the face of it, it looks like the explicit songs do tend to be more energetic than the non-explicit songs. But we can do some stats tests to find out, make this idea precise. This is another kind of plot that's helping to examine whether we will be able to meet the expectations of a t-test that our data is normal. Now, the results of this plot aren't that good. If it was perfectly normal data, it would match a normal distribution and all of these data points would be on this red line. This is called a QQ plot. Typical way of just visually measuring the normality of the data. The way it works is that the percentiles of a normal distribution are kind of matched with the percentiles of the data set. And if it's linear, then it matches the normal distribution, even though it might be bigger or smaller or centered somewhere else. And if it's not linear, then it's not very normal. So you can see it's in the middle of the data set, -2 to 2, or in the middle of the data set, it tends to be normal for both. A bit of a kick here for the explicit songs. Towards the end, not very normal, it falls off rapidly. So you can see the kick there in explicits because of this little bump. So the explicit songs, it does look like a bimodal distribution really. So we're probably violating some assumptions here, but we can run the test anyway. T-tests are fairly robust. If we were doing this for a publication, we'd probably have to justify why the t-test was a good choice for this one, given how bimodal that explicit song energy data looks. But let's run a t-test. So the way we run a t-test here is not going to be very hard. We just say, get this t-test, independent samples t-test, because we're looking at separate participants. Each song is a participant in our study, and we measure its energy. Separate observations, and we run that down here. Most of the rest of the work is just to find out, separate our songs into two groups. So the first group are ones where explicit is 0, and just taking the energy statistic, energy column. Second group is ones where it's 1, taking the energy column. So let's look at those results. So we've got 162,000 non-explicit songs and 10,000 explicit songs. So vastly different numbers of songs here. Only 10,000 are explicit. This means that we really need to use a specific version of a t-test, which is Welch's t-test, where you can have vastly different numbers of data in each group. So we've run Welch's t-test. You run that by setting the equal var equals false in the independent samples t-test function, put in your two groups, and print out our statistics. So the difference in means is 0.1, and the t-statistic is -45, and the p-value is 0. In fact, the p-value is really, really small here because we've got so much data. It's actually affecting the kind of the outcome, or it's making a very small effect, potentially small effect, show a very strong t-statistic showing. And just plot the difference with a box plot as well. You can see that the explicit ones definitely do have higher energy in a box plot. If this was an HCI study, I would be looking a bit askance at this box plot because the boxes are very close and they're mostly overlapped. But because we have so much data, the t-test is able to make a more optimistic judgment about this data set, about its the potential for this finding that the explicit songs have higher energy as being random. So it's making a judgment based on the amount of data it is with that p-value, which is how these things work. We can actually calculate our degrees of freedom here. The degrees of freedom for a normal t-test is pretty easy. It's just the number of data in the first data set plus number of data in the second data set minus 2. But if you're using Welch's t-test, you have to do a different, more complicated equation. It's not that complicated, but I don't want to explain it. The Welch-Satterthwaite equation. So we can just use that and find that our degrees of freedom is 13,000. So we have a lot of degrees of freedom. Let's muck around with our data set and make the degrees of freedom lower and see what happens to that p-value. So I'm just, instead, right up here somewhere, I've got a bit where I can eliminate data. Here we go. I'm just going to take 500 samples instead of 1,000. And check that. So let's do the same plots. We still see this difference in explicit and non-explicit, but we have much less data. If I was more clever, I would have taken a random sample, just an even number from each group, so I could have done a proper independent samples t-test, but I won't try to low code that now. Now we've got a much lower t-statistic. The p-value is still only showing 0. I wonder if we can find a number there. Oh, we've got a number. So it's well under 0.001. We still have a really good number of degrees of freedom, so the p-value can be very low for that t-statistic. We can reduce the amount of data even further and see if we can get this to fail. Only 200 samples. Let's check things. We still see that difference in the means, although the mean for this one is likely to be over here somewhere. And we can run the t-test again. Now we're still below 0.001, but it's starting to get a bit more dodgy. They're still overlapped a little bit. Where's our degrees of freedom? We only have 29 degrees of freedom. Let's reduce this even further, just down to 100. Whoop. I mean, normally you wouldn't do this. You'd use all the data you have. I lost my important line of code. What did I do with it? Okay, down to 100. Check out our histogram again. Still see that difference in mean. Let's see if the test still comes back good. Now we're only just below 0.05. So it's still saying that it meets the alpha less than 0.05 criterion, but doesn't meet 0.01. So we're starting to reach the limits of how few samples we could to demonstrate that effect. We've only got 8 degrees of freedom left. So as we reduce our number of data points, we're increasing the p-value there. Go back to a lot of data. Maybe I won't use everything, but just 10,000 for our later tests. So that was our t-tests. Oh, paired samples t-tests. For this one, we're going to take the same tracks and look at some different measurements on those tracks. So the hypothesis is that the danceability and the valence differ within the same song. I guess the danceability is sort of like how, how rhythmic and dancey a song is, and the valence would kind of be whether it's happy or sad, I think. Let's look in this big list. It's yellow. I'll find the yellow list somewhere. Data, valence, musical positiveness conveyed in a track. Well, that's good to know, that some of these tracks are musically positive. Where am I? I'm lost already. Let's test. So we've got a mean danceability is 0.5. The mean valence is 0.5. The mean difference is very small, 0.0091. We can see that mean difference in our data set. Most of the mean difference is only just a little bit above 0, but it's still enough of a difference for our t-test, paired t-test, to be able to find that out. It's a bit of an unusual way to test this data. Maybe I wouldn't run this test again. Really, we should be looking at like different parts in the same song or something, seeing how the danceability and valence change over time. Anyway, we'll move on to some other measures in a minute. Back to our slides, I think. And move on to ANOVA. We'll get to ANOVA in a minute. So far we've been looking at situations where we had two groups or two things to compare. But what if we have three things to compare? I mentioned before that there is an approach for comparing the means of three groups just using t-tests. You can do what's called pairwise t-tests. So group A, t-test with group B, t-test with group C, and group A, t-test with group C. So that can let you find out if there's significant differences between them. But because we've run three t-tests there, our possibility of encountering a random error is multiplied. So if our alpha, or our boundary for deciding on significance, was 0.05, then that means we're looking for a lower value, a lower than 1 in 20 chance that we've encountered random data. But if we're already doing three tests, then now we've only got a 20 divided by 3 chance. So the issue is going to be that if you run more and more t-tests, eventually you'll get more than 20, and then it will be kind of likely that you may actually have discovered a random effect within that sequence of t-tests on your data. There's an amusing XKCD comic about this, but I forgot to put it in the slides. I should go back and do it later. The solution for that, you can do pairwise t-tests. The solution is to use a correction, which will basically divide or multiply your p-value by a number varying with the number of tests. So this could be good. You can do the pairwise t-tests, but it's bad because your p-values are all getting bigger, and that means that it's harder to establish significance with the same t-statistics and the same number of degrees of freedom. There are better approaches, and the better approach is to do a test which can cope with all of this data together rather than doing multiple independent tests. So if you have 3+ interface variations, or any number of multiple pigeonholes for your data, like all of these multiple mailbox doors, then we can use procedures called analysis of variance to cope with that. So just as an aside here, the ANOVA output is called the F statistic. So sometimes it's called an F test, and a t-test is a t-test. Now there are different kinds of ANOVAs. We already know about different kinds of t-tests. There are different kinds of ANOVAs, and things can get a little bit complicated because now we're talking about the potential for multiple groups or doing a within groups study, or having multiple independent variables, so not just one thing changing our results, and we want to figure out which of the inputs to our experiment, for instance, like two independent variables might be changing the background color of a website versus changing the font. So they're two different independent variables that might lead to some improvement in usability, however silly that might sound. You might have multiple independent variables or even multiple dependent variables, and you want to analyze it all at once. So you have to be very careful with these more complicated situations, that an experiment is designed carefully so that the statistical analysis will be valid. Because, as I mentioned before, just running multiple and multiple t-tests, although that can sort of technically establish significance, it might be very wasteful of the data you have. It might not be using it to its best effect. And because these things get complicated, the API starts to get complicated. We're not just sending two lists of data, list-like objects to a function to do a statistical test. We end up with some quite complicated things I'll show you in a minute. The types of ANOVAs have funny names. The first one, the normal ANOVA, basic ANOVA, is the one-way ANOVA. So this would compare the means of two or more groups with one independent variable. So maybe we've got 3 or 5 groups of users, maybe they're 5 age groups or 5 degrees at ANU. We put them all into different groups, and we are giving each one or measuring their performance using an interface, and we're trying to work out if that effect of age or the effect of degree type is having an output on is significant on our performance with an application. A factorial ANOVA is when we have 2 or more groups and have multiple independent variables. So this would be the situation where you have maybe some of the groups you've split people into groups and they're seeing different kinds of backgrounds, different kinds of fonts, and different kinds of menu ordering. So that would be 3 independent variables. So that would mean that you'd have a lot of different groups. Each one would see only one combination of those variables. Then another option would be your repeated measures ANOVAs. So this would be where you're studying the same group with multiple observations, seeing each of your interface types. And then finally, a multivariate ANOVA or a MANOVA is where you have multiple dependent variables. So you're comparing multiple means, multiple for each observation, more than one response variable with different or the same groups. So ANOVAs can certainly get complicated, as we'll see in a minute. Some assumptions about these tests. This applies both to t-tests and to ANOVA. There's this concept of how the variance of these groups should work. So it's not just that the data is normal, it's that the variance should be homogeneous between your different groups. There's a kind of test you can do to work out how homogeneous the variance is, but won't cover that here. You can look at that in other ways. If it turns out that the data is weird, there's non-homogeneous variance between the groups, you can use some kinds of transformations to make things work, which we don't cover. But again, there are these assumptions that need to be taken into consideration. Statistical tests are not something where you just, particularly for tricky ones like ANOVA, it's not something where you would just look up the API and kind of blindly apply the first thing you find. You would typically have to learn about the test, learn what the options are for calling that API within the programming language you're using for it, whether it's R or SPSS or Python, because you will have to justify these decisions when communicating the research. Some ANOVA examples. So again, we can do our basic ANOVA with scipy.stats. This is the software we've been using so far. We would take some different groups. Maybe we would get a list of groups for all of the different values of this independent variable. This might be a code like group 1, group 2, group 3, group 4, group 5. and we would be finding the output variable, which I'm just calling dependent in this example. So groups is now going to be a list of data, a list of lists, where each list is the data from a different group. Then we can simply use the F one-way ANOVA test on that sequence of groups. So far, so good. This is easy, right? Well, unfortunately, it gets more complicated because I don't think you can do factorial ANOVAs in the stats model, the stats package, scipy.stats. Maybe you can, but there are often other more complicated ways of doing this. The way I'm going to show you here uses this stats models package, which requires you to build a statistical model and then run a test on it. So this is the more kind of advanced way of doing this, is that you define a model for how a dependent variable would vary in comparison with independent variables, fit your data to that model, and then run a test on the model output. So here we've got a model, OLS. I've forgotten what OLS stands for, but this is the function that lets us build the model, and we've got a text description of the model, and the text here is in the format, I think it probably comes from the S programming language, but it was also used in R, a format for describing the relationship between different variables in a data frame. So these are going to be columns, and that's just a regular column. The C means the column is being treated as categorical. So dependent is the dependent variable, and independent is the independent variable. So we want our model to measure how the dependent variable varies with the independent variable. And then call the fit function on that, and that does its work. And then we produce this table of results, the ANOVA table, where we use the ANOVA, I guess that means for a linear model, an ANOVA procedure for a linear model with a model object, and we're using a type 2 ANOVA, and it's beyond this lecture's scope to explain what a type 2 ANOVA is, but we'll just trust me that's the way to do it. Now that doesn't seem that hard either, but in the next one it gets a bit trickier, because in this one we want to have two different independent variables. So when we're measuring two different independent variables, we need not just to have the dependent variable there, the two independent variables there, ind1 and ind2, and we're using like plus to mean that we want two separate effects. We also need to have the interaction effect between those two independent variables. So this is more complicated. We have to remember how to do this and know what kind of statistical model we want before we fit it. Then we use the same procedure on that to run the ANOVA. So this is a more serious situation for ANOVA. Let's have a look at how it might work with our data. So I've reduced our data set, so we might find that things don't work very well, but we'll see what the values are. Okay, so we're looking here at testing whether the key of a song has an effect on the tempo of the song. So our hypothesis is that there's some effect of the key on tempo. And our key is one of 12 different groups, because there's C, C sharp, D, D sharp, E, F, F sharp, etc. There's 12 of them. So our list of groups here is going to have to divide all of these songs up by their key. We have that data in our Spotify data set, and then get the data in a list of series containing just the tempo. So we'll just see what comes up with groups. There we go, here's all of our data frames. All of our arrays within that list. And then we can run we're running the normal basic one-way ANOVA f-test from scipy.stats. Well, if you're very lucky, that'll be all you ever need if you're doing complicated HCI studies. So this one works. We've got an F statistic of 2.56, and we've got a p-value of 0.003, so it's going to be less than, let's take our alpha as 0.01, a decently low alpha. So that would mean that there is a significant effect of tempo because of the key of a song. Let's have a look with the same test, except with this more complicated procedure with the stats model package. So the tempo is the dependent variable again, and we're looking at the key as the categorical variable. It's a little bit more convenient here because we don't have to do this weird group by splitting up into different series step. This the stats model package can deal with the whole data set, the whole data frame, and just pull out the data it needs based on our specification of the model. So let's run it. What have we got? This is giving us a bit more information, and useful information, in fact. It's telling us the degrees of freedom for our test on the effective key, on the dependent variable, tempo. We say we've got 11 degrees of freedom, that's good. We've got a F statistic of 2.56, and we've got the same probability, same p-value, 0.003, so less than 0.01. So that's great. We've actually got another bit of information here, eta squared, which would be the effect size due to that, that key. And that would be telling us that, well, even though there is a significant effect due to the key, it's a very small effect. So this is giving us significantly more information than the t-test, because the t-test was just telling us significance. But the ANOVA is telling us significance and giving us the size of that effect based on the model that we've built. So the size of the effect here is only 0.2%. Actually, it says here 2.5%, but it's 0.2%. 0.28% of the variance in tempo is explained by that key. All the rest of the variance in tempo is unexplained. So it's just 99.7% of that is just unexplained error. So we're getting some more useful information. We can look at the tempo distribution, make some plots. You really can't see much difference in those tempo, depending on the key. But the ANOVA test has found that there is, in fact, an effect. So it's a useful model. Now, how about a factorial ANOVA, two-way ANOVA? So does a song's tempo vary based on the key and or the mode, whether it's major or minor? So we've got 12 levels for the key and only 2 levels for the mode, minor and major. We can use the same data. We don't have to do any changes here. We just have to change our model. So we're measuring tempo as the dependent variable, key, mode, and then the interaction between key and mode. The interaction term here means like maybe there'd be a situation where there's no effect due to tempo, there's no effect due to mode, but when mode and tempo are both working in a certain way, there's an interaction between both of them that will cause an effect. So the ANOVA can help us understand that. Again, we'll run the same table and see what happens. So we get the 11 degrees of freedom due to key, 1 consumed by mode. I guess it's 11 because it's got 11 options, so it's consuming 11 degrees of freedom. And then there's 9,000 residual keys, degrees of freedom. The more levels you have in your data, then the more degrees of freedom would be consumed by the ANOVA test, because it's doing some kind of comparisons between means, between each level of data. So typically you would report both the number of degrees of freedom used by the test, 11, and the residual leftover degrees of freedom. So we can see that we still see a significant effect due to key. We don't see a significant effect due to mode or due to the interaction between key and mode. So good to know. And we're still seeing that only 0.2% of the change in tempo is due to key and very small amounts due to those other effects. So we learn more. And we can do some more charts if you want. And there's a repeated measures ANOVA, which is unfinished. Maybe next year we'll get to do that. I don't know how to do it in this this stats model package. I've done many repeated measures ANOVAs, but always with the R programming language. In fact, I think I've done few ANOVAs with Python for real research. I might have done like a one-way ANOVA, probably not a lot of complicated ANOVAs. Anyways, there's some ANOVA examples, so that's good to know. What's next? Identifying relationships. This is a bit more of a talking part of the lecture, and my little light has just turned off. What happened to my little light? I don't have a plug for it either. Oh well. Maybe my other light will work. No, I'm out of lights. Should have charged all my lights before the start of the lecture. So, when we're identifying relationships, this is when we've got two continuous variables and we want to understand if there's a relationship between them. So the word that's usually used for this is correlation. And there are measures of deciding whether different variables are in correlation and what the direction of that correlation is. So are they positively correlated or inversely correlated? And there are also was important to understand that these measures, although they can give us some information about our data, it's not always indicative of a cause and effect relationship. So the old adage is correlation does not imply causation. And this can certainly happen with typical HCI studies. So the normal kind of correlation measure is Pearson's R, which would have a range of -1, meaning fully negatively correlated, to 1 positively correlated, and 0 is no correlation. Then there's a coefficient of determination, R squared, which is giving us a percentage of how much the variance in one variable is inferred by the other. So that can help if you're maybe have already established a relationship and you want to explain how much your output is very correlating with another value. So just as an example of correlation and causation, if we were studying, for instance, how people use a shopping app, online shopping app, and we were understanding measuring their time spent using it, that might be their performance. So people might have a lower performance if they spend a longer time before they make a purchase. We could find that folks with a higher income tend to have lower performance. So we might find those are negatively correlated. But it turns out that there may be another variable at play because, for instance, the age of a person using an application may result in them having a higher income. Older people tend to have a higher income, but older people might be less familiar with online shopping platforms. So the increase in income is not causing their low performance. It's their age which is causing both of those factors to change. So the correlation that you observe may not be caused between those two variables. It might be random, it might be caused by a different variable, or you simply may not have enough information to imply that connection. Regression is where we would be modeling the connections between two continuous variables. So similarly to, we often think of regression in computing in terms of machine learning, where we think of regression as building a model that will produce more outputs. So if you have one variable as the input, another variable as the output, we want to build a statistical model that will then produce more outputs provided with other inputs. The same concept can be used in statistical modeling, but this is typically where we would be looking at that relationship again between those variables, looking at the percentage of variance and looking at how they're correlated rather than trying to predict new data from new inputs. Another concept here, non-parametric statistical tests. So there'll be lots of situations where our data doesn't fit the expectations for T or ANOVA. One of the situations might be that you've got something like categorical data, so things that are not ordinal, like yes or no as an answer, or do you prefer the red app or do you prefer the blue app? It's categorical data which doesn't have an ordering. Like a Likert scale might be ordered. It might have a kind of natural parametric interpretation, whereas something like yes, no, or red, blue, yellow doesn't have a parametric interpretation. So we have other kinds of tests that can help us to deal with that. Some of these, in some situations, these tests are kind of related to t-test and ANOVA, so it makes sense to look at them together in that context. If you've got data from two independent samples, the test to use would be the Mann-Whitney-U test, a very classic test. If you've got two data sets with the same user group, so again, paired samples t-test is the equivalent, you could use the Wilcoxon signed rank test. And if you had three or more data sets or three or more groups, you can use variations on the ANOVA procedure. One's called Kruskal-Wallis one-way ANOVA. If you've got dependent or two-way ANOVA situation, you could use Friedman's two-way ANOVA. They're modifications of the ANOVA procedure. One that I've had some experience with is this, for more complicated factorial ANOVA situations, you can use an transformation on the data, the aligned rank transform on the ANOVA. It was very famously written about by someone called Jacob Wobrock in 2011. Had this great paper about saying the ART ANOVA is going to solve all our problems. Very widely cited paper. And then only today, I discovered that this is not agreed by everyone. There's this paper, I guess this is under review, but the illusory promise of the aligned rank transform. And boy, it's leading me to question my life choices in some ways. Although all I did was follow the best advice and probably have not made any terrible mistakes. But this paper is making some claims that the ART, the aligned rank transformation, is not as helpful as argued initially by Wobrock. And it's unfortunately, if this paper is true, ART transform is very widely relied on in HCI, so people will have to find some alternatives there, alternative non-parametric techniques. Another important test, we'll look at this one in some detail, is the chi-squared test. So this is useful when we have categorical data that doesn't have an ordering. So something like yes or no, or blue, green, yellow, red, or choice of preference between two apps. We might have some data like this, where you've got two groups, and group A has said yes 5 times and no 7 times, and group B has said yes 11 times and no 1 time. So if you have some data like that, you might say, well, look, the Bs definitely say yes more than the As. But that's a significance judgment. That's a hypothesis on this data. So can we make that precise? The chi-square statistic lets us make that precise, and it's very widely deployed in that kind of situation where you've done surveys with people about their preferences or about their use of an interface. So in this case, the chi-square statistic is 4.6875. Again, not very useful until we have the number of degrees of freedom. In this case, it's 1, which is what's left after we cope with the number of questions we're asking of the data and the amount of data we've got. And that leads to a p-value of 0.03, which is less than 0.05. So we are seeing a significant, this supports the idea that this table has some significant data in it, that it significantly differs from the average noisy response. I guess if we had a noisy response, we'd expect even numbers to say yes and no, much like they do in group A, and there would be even numbers in group B. Let's have a look at this in terms of our data set. I've got whoops, failed to discard changes, that's bad. Here's a chi-squared test. So we can say, is there a relationship between explicit content and the mode? So the explicit was a yes-no flag, and the mode, major, minor, was again a yes-no flag. 0 or 1. So we can make a table for that, a contingency table from our data set. We've got the mode being major. 6,000 songs were major for non-explicit, and 2,000 were minor for non-explicit. The explicit data set is much smaller. We've got 200 major, minor and 400 major. So we can run a chi-squared test with that, and the chi-squared statistic is 36, degrees of freedom 1, and the p-value is 0, so it's very small. So it is a significant difference between those values. And this was my little example with 2 groups and 2 answers. And that's the end of my notebook. This one's in the GitHub repo for the lecture slides, so you can go and play around with this if you want. Where's the rest of my slides? Back to the slides. I've got a few more slides just to show you a short case study. So I wanted to just discuss a piece of research that I'd done that involves some quantitative data. Actually, in the last few years, we haven't done as much, or the last year or two, haven't done as much quantitative data studies as I used to during my PhD and shortly after in my postdoc. I was really interested in trying to establish some empirical bases for evaluating different kinds of musical instruments. These days we're in my lab, more interested in qualitative analysis and have looked at more deeply into using thematic analysis and interview techniques. But I can show you some example, or one example where I did use quantitative data analysis. So in this study, this was understanding musical predictions with an embodied interface for musical machine learning. I was interested in studying how people might improvise with a artificial intelligence integrated interface, which was this little box. And the little box had one lever that you could pull and move that up and down. It would go wee woo when you move the lever. Then when you stop playing, it had an AI model in it that would start playing, responding to or continuing what you'd done. And the little AI model would go wee woo as well for its performance, and it would also wave its little lever as well. So the human got to control one lever, and the AI system got to control one lever. So I was interested in 2 things. One, what was the effect of different machine learning models on people's performances with this simple musical instrument? And what was the effect of the feedback mechanism of having that motor running? So to run this study, I got participants, and each participant would do 6 different improvisations under different conditions. So the way it was designed was that there were 6 conditions. There were 3 different machine learning models. One was trained on data from me doing a performance with it for about an hour and using that as a model for the system's performances. Another one was a model based on some synthetic data of just like slow motion back and forth. And the other one was just a random model. It was untrained, just noise. Then there were 2 options for the feedback mechanism. The motor could be off, so they would just hear the sound of the machine learning system, or the motor could be on, so the machine learning system would wave its little lever as well when it was performing. So each participant would do their one short improvisation under each of these 6 conditions. So they did 6 improvisations. So this means it was what we call a 3x2 design, because there are 2 different experimental factors or independent variables. One, the motor, and the other one was the machine learning model. There were 3 levels for the machine learning model, and there were 2 levels for the motor. That means that there were 6 conditions in total. So this was a within group study because each person saw each of these conditions. I had them do it in a different order to balance the learning effects. So we would survey 8 aspects of these performances. So after each performance, they'd do a little survey about what they'd experienced. And I also measured how long the improvisations were. So that will be interesting in a minute. So let's look at some data. In the research paper that I published after that, I had these 8 questions with the quantitative data represented in these box plots. I was using a 9-level Likert scale. I like using 7 or 9 level Likert scales for my survey questions because I just think it tends to mean that the data is not just clustered around the neutral area. It gives you some more levels to see variance within people's responses. So this is the 12 responses for each one of these situations for each question. You can see the ones with the servo off and the servo on. Servo off's blue, on is orange. The human source data is here, synth is in the middle, and noise is on the right. So some of these are a bit, you have to know what the questions were to see what it really means. But for folks who were, for this question it was like, did you feel that the response was related to your input? And with the machine learning model, they definitely felt it was not related. So that tends to be lower on both, whether the servo was on or off. For the synth, it tended to be in the middle somewhere, and then for the human data, they tended to feel that the machine learning response was related to what they'd been just doing, which was true. It was supposed to be related. So good that we saw that effect. Overall, folks generally felt about the same, that they understood the data, understood the responses, so even with the noise model. And they generally felt that the human model with the servo off was the highest quality here, just looking at the box plots. But we can have a look at the analysis of this data. This was analyzed with the ART ANOVA procedure and then pairwise t-test to work out which was the highest one. So I'd work out which factor had an effect, if it was a significant effect, and then use pairwise t-test to establish which level of that factor was the best or worst. So I didn't see any impact on these results due to the motor changing, the servo being on or off, which was unfortunate. I was hoping to see that, but didn't see it in the data. So just had to report that. The change of ML model did have show some significant effects on question 2, question 4, 5, 6, and 7. So quite a few questions. 5 of the 8 questions. For instance, question 2 had this big change between the human model and the synth model. So they definitely, the pairwise t-test showed that the human model was the most related and the human model was the most creative on question 4. And the noise was the least related and the least creative. And one other takeaway from this data, just looking at the box plots, was that the noise model, even though it was just random numbers, was not rated that badly. And I was observing as I was watching people do their performances that folks would really try to figure out what the noise model was doing and try to move in a certain way to get it to do something. And of course, it was just random numbers, so it would not do anything, sadly for them. But they kept trying. The performance length was the other measurement I did. I did run significance tests and didn't see significance tests on this one, but we can see something from the box plot. So this shows a limitation of significance tests. They're only showing you one aspect of data, which is whether the means are different. And we started this lecture with that hope that we'll be able to establish differences in means. But in this, we're seeing a difference in the variation in the data. So the box plot for the servo is wider, more variation in lengths of the data with the servo on and with the servo on, except for the noise model when there's more variation in the data with the servo off. So the explanation here was that perhaps with the servo on, it was a bit more polarizing. Some people tended to do a longer improvisation and some people tended to do a shorter improvisation. The servo off with the human model, people tended to do a similarly long improvisation. Similarly with the synth model. With the noise model, people tended to do very shorter improvisations when the servo was on. When it was off, some folks were really exploring it, going up to the upper limit of 5 minutes improvising. So the takeaways here were that the physical representation was a polarizing factor, maybe not the best way to study it, but did see some evidence of that in the data. From interviewing the performers and observing them performing, I saw that they were really working hard to understand the ML model and influence it. But it was certainly clear that the constrained model could produce a compelling experience, even in this silly little single lever synthesizer. So I just wanted to explain this case study just to show how a significance test can be used in an HCI context. One of the limitations with this study, and many of the studies that I've done, is that with a reasonably small number of participants, in this one I had 12, so that's again, that was the mode for Chi overall, right? Most common is 12 participants. Your degrees of freedom will be quite low when dealing with statistics tests. That means that even if there is a real effect due to one of your independent variables, it can be hard to demonstrate statistically that there is a significance due to that effect, because you don't have many, your number of degrees of freedom would be low. That means that your p-values would tend to be inflated, and you won't see the significance that you might be hoping for. So if I had 100,000 samples and had the same box plots, there would be lots of significant differences to analyze. But with only 12, the tests are quite conservative, showing its significance. So that can be problematic with HCI, but it's certainly possible to show some things and derive some findings from the plots as well, or different aspects of the plots, not just the mean. And that's the end of the lecture. So this one was, I guess we'll be doing a few shorter lectures. Oh, I love statistics. I'm just going to read some questions. Someone's watching this in the cinema. That's good. There is statistically significant positive correlation between the number of films that Nicolas Cage appears in and the number of people who drown by falling into a swimming pool, particularly in the US between 1999 and 2009. Well, that is interesting, problematic. I guess one of the concerns with statistics is that you do, with very large populations sampled, you can sometimes show some weird things. You can find weird correlations. You can find weird, statistically significant relationships that still don't seem to be right, and they're probably not right. Like, we know that it's a good joke, but Nicolas Cage is probably not having an effect on the number of drownings, even though we see that in the data. And again, this is one of the dangers of systems with very large amounts of samples. People are doing some p-hacking, another thought in the comments. You can do, p-hacking is when we do many tests to figure out which relationships are significant. So that can again work with very large data sets where you have a lot of variables to compare. The corrections, like the Bonferroni correction, is supposed to protect us a bit against p-hacking, but you can certainly do that in science, and people have used those techniques in weird ways. Another classic in HCI, particularly where we've got these low sample size, is using a statistical test, getting the output. It doesn't meet any of the usual requirements for significance. It might be 0.051 or 0.055, and people will write things in their papers like, oh, it was borderline significant. And I think you could go through some of my papers, and I probably have written something like that too. This is partly why when I'm dealing with small sample sizes, I just use qualitative data, because it's really, the quantitative data can be very hard to get a good result. And I've learned from sending papers in and seeing them reviewed, even if I've got both quantitative and qualitative data in the same paper, if the quantitative data has problems, the reviewers tend to be really laser focused on that and shooting you down. So there can be some really problematic issues with research, which is quite reasonable in the qualitative aspects, but the quantitative is easy to pick apart because of these quite strict and clear lines between a working analysis and non-worthy analysis. I'm not going to meet you at the bar. I have the same slide for my questions as I do in the Canberra Cinema. Normally we meet at the bar after the cinema lectures for a discussion and questions. I'm not going to do that here. If you've got a question, you can put it in the chat. Otherwise, put it on the forum later. I'm going to stop the lecture in a minute and go home. I will be back on Monday in Canberra Cinema to do the second last lecture. We're almost at the end of HCI for the semester, which is fairly exciting for me because it's been a very busy semester. We've had to develop all of these lectures from scratch, or mostly from scratch. I did have some previous work I'd borrowed from colleagues, but I'll be publishing this when we get to the end. I've got a count slide script, which shows how many slides there are in the whole course. So far, we've got 485 slides in the course, a total of 31,000 words across all of those slides, probably including all of those markdown tables as words, which is a bit naughty, but I'll work on a better word counter. So this one was a bit of a short lecture, 35 slides, only 2,000 words. The longest lecture was the interfaces lecture. That was a biggie, 5,500 words. Woo, that's a lot. Followed up by the design lecture, which was a massive lecture as well, 55 slides, 3,000 words. So we've got another 2 lectures to go, probably about 40 slides for each one. So we'll probably end up with something around 560 slides total in the class developed this semester. So it's certainly been a marathon. I need to do another analysis of all of the workshops we've written because most of those also had to be developed from scratch. So a very, very work-intensive semester for me and the tutor team in this class. Surely I should stream the next lecture too. You folks love streaming, but people love going to the, other people might like going to the theater. Maybe I should bring my stuff, my streaming gear to the theater and just stream it live from there, hey? I'll wait and see if there's any more questions. Would sound and music computing be running next year? I am terribly sorry to disappoint you, but I've been informed that I am not going to do sound and music computing in semester 1 next year. We're thinking about that course as being doing it every 2 years. So we ran it this year, and we plan to run it next in 2027. So if that doesn't work with your degree, I'm super duper sorry. Can I get an HD because I'm Comp 3900 biggest fan, please? Yes. The person with the UID, you Comp 3900 biggest fan 99, will definitely get an HD. I'll put that into our marking system. If that's not your UID for reals, then sadly you won't get an HD. All right, folks, I'm going to roll up to the ending screen and catch you folks on Monday. Thanks for a great stream. It was wonderful to catch up with folks again online. As I said, I do like teaching online. I don't know. I don't know how to square this circle. I had a great time teaching online during COVID. I do have an outro. Man, you should go back and watch my 2300 and 1720 lectures. There's intros, outros, interstitial music. I'd take a break, we'd have a thing. I've got 2 camera setups. I'm not anything like a pro, the super pro streamers, but it is fun to set up some cameras and scenes in OBS for lectures. It's a kind of life concern of mine that the quality of the streamed lectures as a video is just so much better than the quality of Echo 360. But at the same time, it's really wonderful to get in the room and speak to students face to face, and we get some really natural questions and discussions happening. But I don't know, is there a way we can make it work, everything work at the same level? I don't know. All right, folks, I'll catch you next time.